starting the recording and back to business. So previous RS-232 and the extension, hardware extension 485 are basically very still common transmission. This RS-232 type transmission is still used between, say, microcontrollers on the same board. So if you are continuing your studies mostly with these smart systems, you will meet Joe and Keijo. Oh, you have already met Joe and Keijo. They will teach you a lot of these how to apply serial lines and also the serial interfaces, other serial interfaces, and especially I2C. You will be familiar with those. The I2C interface is very popular on the sensors as a sensor interface. Lots of digital sensors actually communicate using I2C. Why? This is actually why. On I2C, I2C stands for integrated circuits. So between integrated circuits bus. It's relatively slow speed, but it's addressed line. So the slave devices have an address. By default, it's 7 bits, but extended address range is up to 13 bits on one single data bus consisting of 2 lines. Then the normal data rate is 100 kilobits per second, maximum distance less than 1 meter. So within one printed circuit board or between two circuit boards which are very close to each other. This 1 meter is actually limiting it. The 2 lines, one line is serial data and another one is serial clock. Both lines has pull-up resistors. So basically all of these devices, if they want to set data to the bus, they will just have a transistor, either NPN transistor or N MOSFET, and it draws that line to the ground. And when you want to write 1 on the line, you just release the switch. Simple. It doesn't get much simpler than that. So pull-up resistors. What size pull-up resistor? Well, actually the another standard that's not standardized that much. It depends on the electronics designer. Usually, was it 220 ohms or something like that? However, I2C is used in small electronic devices, especially on the sensors, but like temperature, humidity, position, light, color, brightness, whatever, you can find a lot of different sensors. But on the other hand, it's also a favorite bus for EEPROM memories, for example, for calibration data. Small EEPROM, say 1 kilobyte EEPROM on I2C bus, and basically you can read and or write the calibration or log files, or even actually use that one as a boot code. There are some microprocessors which can be booted from EEPROM. Okay. Additional things. Laptop battery. If it's from this decade, well, 2010 and later. It's connected using SMBus. It's a smart battery connected with the SMBus, which is very, very close to I2C. So actually some say that SMBus is an extension of I2C bus. And this is the place where the computer checks what kind of battery make and model it has and what is the current charge level. So it's a smart battery. And then you can have these fancy software locks that you cannot change your battery yourself. Unless you fake it. But anyway, I'm not teaching you much of hacking on this course. You must attend some other course. Well, that would be nice, fun, having a electronics hacking course. HDMI cables actually also have I2C interface that connected devices can identify each other. So it's basically the consumer electronics control. So a couple of those wires on HDMI cable is reserved for I2C communication. So now we are not talking about something that was past and just some of that history. Some of the modern world is based on that historical thing. But okay, even those historical things, they have plenty of use still. But I2C is really a decent bus. It's rugged, simple, it works and doesn't take much of electronics. Also, I2C communication, although it's I think it's owned by Philips. The intellectual properties actually owned by Philips, but still it's you don't need to pay royalties if you tell actually it's two-wire bus, not I2C bus. Okay. Anyways, it's not that rigorously let's see. It's not that rigorously followed how many people how many companies are using the same standard. Okay, it is a loose kind of loose intellectual property. Okay, that's the simple I2C communication. There are bits. Okay, 2 lines, serial line, and the serial clock line and the data line. Okay, the serial clock line is the higher one, serial data line is the lower one. There's still a mistake on that one data sheet, I see. So the serial clock is the higher one, which looks like a clock. Serial data is the lower one. And the start condition is actually when clock is still high and the data goes low. So data goes low first and clock is high. That means now we start sending. Immediately after that, there's a most significant bit first, 8 bits, and first the first 7 bits of that 8 is the address byte, followed by the write bit. So write is 0 and read is 1. So if that is right, then actually that address device should start listening and reading. If that is a read bit, then on the next byte that device which recognizes the address will start reading stuff, start setting stuff on the line. Okay. And after that, in this case, it was a write and command byte. This particular example is DS1621, which is a I2C bus temperature sensor. Very popular sensor on, for example, inside of your computer. That's most probable sensor which senses the inside temperature of your computer. Or it could be also glued on the what is that, this on the top of your processor, on that processor heatsink, stuck there to measure the processor temperature. Very, very popular component on I2C bus. And yeah, that's how you write a command byte to that one. Setting bitsm. Click, click, click. It works. And then basically after that, the master leaves the data line floating. So after the transmission, both data and clock lines are floating. Stop conditioning. So if that is a stop, then the start, we had serial clock line high when the data line went low. The stop condition is actually we have clock line high again, but now we have the data line going high again also. There, quite simple communication. Okay, this seems to be okay. Okay, it's still telling the same, but a little bit different details. There's the acknowledgement signal. So practically there, when this processor has sent this address byte with write byte, it waits for one clock cycle. So it reads if there's any device recognized that address. If there is a device recognizing the address, then that device keeps that acknowledgement bit there during the clock cycle. Okay. So this way, the sending, which means in this case it's the processor, it knows that data transmission went okay. Same when you are writing data byte, the next data byte, again, it's basically between start and stop. Device has recognized this transmission, then it sends data byte or command byte or as many command bytes as they are needed. And after each 8-bit transmission of data, there's an acknowledgement. And finally, the stop sequence. Yep, plenty of small details, and more about that one will come on some other hardware related software courses in smart systems. Okay, a bit tricky, more bitty, tricky when you want to write a command and read data on one single transmission. So first we have the start conditioning. Start condition meaning clock is high, data goes low. Then we have the address byte with write, wait for acknowledgement. Then we have the command byte, send, wait for the acknowledgement. Then we will repeat the start conditioning, meaning that during the next clock cycle, when the clock is high, or repeated start is right here. When the clock is high here, small details here, I don't know if you can see it or not. When the clock cycle is high, you actually lower this data line. So release it there and then lower it during the clock is high cycle. So it basically repeated start. So it immediately starts the next transmission, which always start with address byte and now we have read condition. And this acknowledgement is set by the device that, okay, I'm here. And then data byte is given by this device, and master, meaning the processor, gives the acknowledgement signal. In here, this case, it's 1 byte transmission, not acknowledged. NAC actually means that end of transmission. And then stop. Okay, tricky. So it's a bit tricky, yes. Question is where's the manual for I2C communication? The answer is, well, datasheet. Down here, if I can just access that, I cannot access it from here. Down here, there is the datasheet, which has 16 pages. Somewhere down here, we can see what kind of commands you are giving that device. For example, command read temperature in this one would mean that you will actually access the address here with the write and have the command byte read temperature, and the following byte would be to the same or repeated start to the same address device, and this would be the temperature byte, the data itself, and everything on that one single datasheet. So communicating with all sorts of peripheral devices using serial port, it requires quite a lot of reading of the data sheets. But someone has to do it, and that's why we have engineers. One set of engineers will write these data sheets, and then another part will read the data sheets. And magic happens. Okay. Arduino and I2C. In AVR MCU, there is a built-in I2C unit, so it's hardware. Arduino also features numerous libraries that make it relatively easy to use I2C. However, these libraries don't work with Tinkercad. I know that's a bummer. I really wish that we had the real in-class laboratories. Then we would have so much more fun. Anyhow, how to use that, there's a link. So if you happen to have Arduino on your hands and want to play with it with, for example, a temperature sensor, that particular temperature sensor, single pieces, I think it's something like few euros. But anyways, the usage is not much different from the serial line, but it's just that you need to read the manual of the device and match your data transmission based on that one, for example, on here loop wire begin transmission for which starts a transmission to device number 4. So device number 4 address on the first byte, then wire write. It means that okay, there's a write bit on that device, and then basically it sends those 5 bytes 1 2 3 4 5 sorry 6 bytes 6 bytes. So X space IS space have 6 bytes. It's a string. So at the end of the string, there's null character. Okay, unless that write actually does it the other way around. Anyways, wire write X sends 1 byte, just that X number, and then end transmission. On the right hand side, okay, wire begin 4, and on join I2C bus with event 4, and well, you can read the rest. There are plenty of examples of how to make things to click on Arduino. This is one of them, and this is really a bummer that we cannot write on Tinkercad. Okay, that was the I2C between processor and multiple peripheral devices. Slow speed, but it works. It's the rugged way of transmitting small amount of information. And it's actually used embedded in lots of consumer kind of applications. SPI interface, another serial port or serial peripheral interface. Now we are talking about asynchronous. There is extra space. It's asynchronous, not asynchronous, but asynchronous full duplex bus. No, it's asynchronous. It's synchronous. Yes, sorry. So synchronous meaning it has a clock, bus clock. And it works between one master and multiple slaves using 4-wire communication. There's a serial clock which is always driven by the master. So master sets the clock. Then 2 lines. Master out, slave in. Carries serial data from master to slave. So microprocessor to, for example, device. Or master microprocessor to slave microprocessor. Then miso is not just delicious Japanese soup, but also master in, slave out. So it carries serial data from slave to master. Simple. Then there's a slave select scene. So each device, each SPI slave, they don't have any addresses, but they have chip select or slave select signals. Generally, those are low active. So when you pull this line low, it's 0 state, that activates that particular slave. Meaning that in this setup with only one slave select lines, you can communicate with one SPI interface device. SPI does not have defined data rates or data content size. It depends totally on the applications and devices. But you can actually get pretty high rate data transmission, say around 10 megabits per second, which is pretty high. And with just tweaking, actually, you can get even 100 megabits per second. But then it goes to high speed your design. But still, the range is very short. But that is enough for the applications where the SPI is used. Okay, with multiple devices, they are sharing the same data lines and clock line, but separate slave select lines. So that way you can actually, the SPI master will control which slave will be in use, one at a time. So yes, a slave will ignore everything on the bus if the slave select is logical 0. And there are some other fine details on how this bus actually works, but those are mostly, as I said on the previous slide, it's based on, well, it depends on the device. So again, read that down manual. Where they use SPI. How about SD memory cards? They are SPI compatible with 3.3 volt voltage levels. And actually, there are several different sizes. There's a micro, mini, normal. Then this, what is MMC? It's the memory card something. And the pins are more or less the same, except the micro actually have some difference in pin. Yeah, serial card select and that kind of stuff. But anyways, if you have a SPI connector, want to connect that one with the microcontroller, start communicating and saving stuff or reading stuff from micro or this SD card. That's pretty easy since it has SPI card select, so that chip select negative logic, SPI data in MOSI, SPI serial clock, and then SPI serial data out, whatever it has power and ground. Okay. And then this basically on memory cards. Pin 8 which is not used, but on SDIO cards, meaning SD card which is not actually memory, that's actually interrupt pin. Interesting. So SD bus is not just for memories. Okay, however, where else do you use the SPI bus? High-speed data converters, since practically there's not much limit on how fast does it go. For example, and such kind of things. Arduino. There is a SPI library. You just include SPI.h and then SPI begin pin mode. Basically, it's you call pin mode and set this chip select for output for that SPI bus, and then you can start writing and reading stuff. Straightforward again to use in Arduino, not a biggie. I would guess also in this case this our Tinkercad environment doesn't have SPI either, but SPI is one of the most straightforward interfaces. Just 4 lines plus common ground, of course. MISO, MOSI, serial clock, and slave select. And again, trick. The communication is easy, but the trick is to read the data sheet, see the protocol, how that device is communicating with any other device, how to read and write data. Okay, so wrap up. Serial port, either real RS-232 or extended version RS-485 or without any line buffering, connecting signals from all the data transmission from one device to another one, those demonstration on Tinkercad. Then we have the ASCII character set, basically gives a nice way of sending human readable information, not just binary values, but human readable information on data transmission, ASCII coded stuff, and then which is actually now more or less called UTF 8-bit universal characters. Okay, then we have these buses which are defined between microcontroller and a device, for example, a sensor, like in I2C, especially I2C bus for sensor. There was the temperature sensor example where the hard part is to read the manual to see how the control logic actually works. But basically the fundamental parts there is start transmission, set the read or write to set certain address, then if needed restart, and then do the second operation. So practically usually so that you first set a command, which is writing a command to a device, restart the bus, and then set the address again to read data from the device. Okay, that kind of protocol. SPI, there you really have to read the manual, but the bus is straightforward, very straightforward bus. But the device can actually be a tricky. Another one actually where the SPI is used quite a lot of these in these communication devices, like there are these commercially available the free low range radio transmitters and receivers. Those devices quite often are communicating using SPI bus with a microcontroller. So that chip itself, because the SPI is fast compared to I2C. Okay, all of those buses straightforward on the code. You just write the code and it does exactly the setting of the bits and pieces. Okay, let's go a little bit deeper on the wires and talking about transmission lines. Real life challenges, what we have been already seeing is that with RS-232, usable distance is 50 meters or 10 meters or so. I2C usable distance is a few meters. Well, how long these the HDMI cables can you get from shop? 3 meters, I think 5 meters max, maybe 10 meters. SPI, that's 10 centimeters. It's fast communication with a high bit rate. Okay. If the bus is too long or the signal frequency is too high, the receiver may not able to construct the received data. And there we have the bit error rate. So bit error rate is measurement of, especially for the local area network, wide area networks, on the quality of data network. For wired Ethernet network, bit error rate, say typical values is something like 10 times 10 to minus 12 bit error rate, meaning that actually you have one error in, let's see, minus 12 would be 1 divided by millions of millions, million times million. Yes, 1000 exponent 4 million. And next one is billion, and this gazillion. Okay, gazillion. So it's pretty darn good. But on the other hand, when you think of how much data there is on Ethernet, you cannot actually anymore, you cannot live with resending it again. Since on these Ethernet networks, depending on the packet size, two devices could be starting sending at the same time. So there could be collisions there. In addition to that, if you have a high bit error rate, you can end up having the congestion of these wires really fast, unless you have the bit error rates really low. So early Ethernet networks had the 10 to minus 10 bit error rates. And now the requirement in most of those is actually 100 times more strict. More stuff goes into Ethernet faster. You cannot afford sending it again. Otherwise, latency goes haywire. Okay, so bit error rates. So those are the challenges. Okay, transmission line. What is transmission line? Actually, transmission line here is something like that. There is a port A, for example, sending. Both of these could be transceivers, both sending and receiving on one single media. That transmission line has impedance. And that impedance looks like this picture here. So there is a capacitance. Maybe I'll now show you, draw you something. Two lines. Usually twisted there, but I've just put them here. Two lines. So this is the port A here. This is the port B. And this is few meters, whatever the length of the cable is. Two wires very close to each other. So if you have seen paired cables, they are something like 1 millimeter apart. And if you have tens of meters of wire, then in between of these wires, you have the capacitance. A little bit of capacitance all over the medium. So usually these typical are values. I think it was something like 12 picofarads per feet. Yeah, I know I should use the meters. So it's 30 picofarads per meter, something like that. sounds just about right, or 50 picofarads per meter. And then we have long wires. Long wires means that it has some inductance on the wire. If the current flows, it generates the magnetic field around it. There's some magnetic coupling between these, so practically it has inductance on that model. In addition to that, the wires are thin because then you don't need that much copper and the wire is cheaper. So basically then on these wires you have serial resistance. In addition to that, you will have some loss, power loss. When you are applying voltage here, there's a power loss on this cable because of that insulator is leaking a bit. So basically it also have this loss resistor in between of that one. Okay, that inductor actually is part of the wire. So that's why the model of any long transmission line looks like that. And again, remember this is a model. Same as on exercise number 3, the loudspeaker model is just 8 ohm resistor. Okay, so 2 resistors to model the attenuation, and then capacitor for line capacitance between the cables, and inductor that models the wire inductance. Long wire, even straight line, it has inductance. Okay, so it has a voltage divider. For DC, there's 2 resistors which are in series. So if you put U in here, you have actually for DC, you have the voltage divider. So the voltage here is less. And then there's RL. RL. So this R, that L is a low pass filter. And so is the low pass filter based on resistor and this resistor and this capacitor. So practically there are 2 kind of low pass filters here. So which means that higher peak signals will not pass through without being interfered. And in addition to that, actually, the third part of this one is the ringing, because this here is oscillating circuit. This oscillates. We haven't gone through the oscillation on or RL circuits in that sense, but that actually will oscillate because this inductor and this capacitor actually have the phase shift on the current. So when current flows that way, actually the voltage here goes higher. And if it doesn't go here, basically it comes back and this circuit here oscillates a bit. Okay, and so this concept of transmission lines explains why high data rates are useful only for short distances. And okay, analyzing transmission lines more than that, that's a topic for electronics engineers, not really IoT, but you just need to understand that, okay, if you put a wire, it really matters what kind of wire you put it there. And if you see funny things happening, it might be that you have a bad transmission line. Now it would be exercise time, but that also means that let's have a short break again. So let's see, did you have any questions? Did I? Oh no, it looks like my Zoom meeting more or less stopped working.